Okay, so we will continue with the new chapter, chapter 3. As you probably have seen during chapter 1 and chapter 2, and even this chapter 3, it's more like basic introduction to thermodynamics. Okay, maybe we haven't done a lot of tutorial exercise or examples yet, because actually those these few chapters, chapter 1, 2, 3, will be actually the fundamental or the basic knowledge that you have to know first in thermodynamics before we can proceed with the first law, second law, thermodynamics that I have talked about during the first week. Okay, so maybe maybe you maybe we don't do much example yet, but because the application or the example is what we are going to do, maybe in the chapter 4 onwards, when we apply the thermodynamics law, the energy calculation, etc., the energy balance, etc. Okay, so just bear with me to at least you have to understand first all of these basic fundamentals in thermodynamics, the definition, etc. Okay, so we start. Okay. Uh, okay. So this chapter is about properties of pure substance. So first we have to understand first what is pure substance. So it's a bit of there's a bit of a chemistry background also. Okay. So that's why in a chemical engineering, one of the fundamental thing that they have to learn also is thermodynamics. Okay, because they also apply a lot of this for chemical. Okay, so pure substance. Okay, this definition. What is pure substance? When we say pure substance, is a fixed chemical composition. Okay, a fixed chemical composition, a substance. Okay, a fluid or material. There's a fixed chemical composition throughout. Okay, so for example, air. Okay, air, nitrogen, oxygen, right? Those are what we call pure substance. Okay. Okay. Even though air, for example, it is a mixture of hydrogen and oxygen, H2O, but it still can be considered as a pure substance because the composition of those hydrogen, oxygen in the air molecule is fixed. Okay, so air is still can be considered as pure substance. Okay, but example, if you have oil and water, minyak dengan air kan, oil and water, those are the combination of both are not a pure substance. Okay, because it can be mixed up, oil dengan water, oil and water cannot be a mixture. Okay, cannot be mixed up. Okay, so it is not a pure substance. Okay, so however, another definition is that a pure substance also can be a mixture of liquid and gas. For example, if you have a water, which is in vapor, the water is in vapor phase, WAP, and at the same time, we also have water in liquid. Okay, so air liquid tu dengan yang bentuk WAP tapi dua-dua tu adalah air, H2O. So it is still a mixture of a pure substance. Sebab this is still one substance. Okay, water. Okay, it's just that the phase is different, vapor and liquid, but it's still a one substance. So there is still a pure substance. Okay. Okay, and then sorry. So phase of pure substance. Okay, so this is the molecules. I think this one you already know. You have already learned this one in SPM, I think. Okay. So these are we can imagine the structure, the position of the molecules inside solid, the pure substance, solid, liquid, and gas. Okay, the A, B, C. A is like example the molecules in a solid. We can imagine that the molecules in solid is more like tersusun lah, in the position kept this way in for example in picture A. Okay, and then B, molecules in liquid phase like water, oil, etc. And then C, the molecules in random, okay, in gas phase. Okay, so it's we assume that the velocity of the molecules, okay, in the gas phase is more is higher. Okay, so it can move randomly secara rawak. Okay. So in a solid, the attractive and a repulsive force between the molecules tend to maintain them at relatively constant distance from each other. So dia ada daya tarikan yang diterkan. Okay, attractive to pull and push each other. Each other means the molecules inside. Okay, next, okay, other definitions. Okay, once we know what is pure substance, okay, once we know what is pure substance, then we have to understand the different process that can occur inside the pure substance. Okay, example always the easiest example always water or air. Okay. Okay, water. Okay, we take water. So the first one, compressed liquid. Okay, or subcool liquid. Okay, so what is compressed liquid? A substance that is not about to vaporize. So not about to vaporize, is compressed. Okay, because normally, okay, later on when you have to apply this thermodynamic concept, you will see, we will look at the engine cycle, thermodynamic cycle, right? In those engine, even in aircraft engine cycle, or gas turbine cycle, power plant cycle, the compression, the process of the compression of liquid or other fluid is always at a lower temperature compared to the expansion, the opposite, which is expansion in turbine. Okay, so that's why this substance, this pure substance, when it is not about to vaporize, okay, it is also called as compressed liquid, because the process that always usually occur during that period, okay, that moment is compression. Okay, compressed liquid or subcool liquid. Okay, and then we also have okay, later on in my next slides there is a diagram. Okay, so in the diagram you will see clearly the process. Okay, right now I just mentioned the definition first. Okay, so saturated liquid, a liquid that is about to vaporize. Okay, so compressed, not yet, not about to vaporize, but saturated liquid, just the moment when the pure substance is about to vaporize, not yet vaporization process, but just about to vaporize. Okay, if you understand the word saturated, sorry, I just explain in Malay a bit. Saturated ni macam at one point tu dia macam dah penuh lah, dia macam dekat atas sekali kan, nak kata maksimum tak maksimum sangat, tapi that is what it's like the at the peak point, something like that. Okay, saturated means, okay, because we also use this term saturation in electrical. Okay, so in here in chemical or thermodynamic, is what we call saturated liquid. It is about when it is the liquid when it is about to vaporize. Okay, because during the vaporization process, the change of the phase of the liquid is different. Okay, so just to be clear, saturated liquid is before the liquid about to vaporize. Okay. Okay, so the first one, state one, at 1 atmosphere and 20 degrees Celsius, water exists in the liquid phase compressed liquid. Okay, so example, water, because we know that water vaporize, the evaporation for water usually occur at 100 degrees Celsius kan. The water boil or vaporize at 100 degrees Celsius. So below or much lower than 100 degrees Celsius, for example at 20 degrees Celsius, we can consider the water is in compressed liquid phase or subcool liquid phase. Okay, we assume that. Okay, so because we know that water always vaporize, maybe for other fluid, I don't know, for example oil, etc. If example, I don't remember the exact temperature for vaporization. For example, if the oil can be vaporized at 80 degrees Celsius, so below 80 degrees Celsius, we assume that the oil is in the compressed liquid state or subcool liquid state. Okay, so we have this is very important because we have to know the phase of those liquid or fluid that we want to study. Okay, so next one is saturated liquid. Okay, at 1 atmosphere pressure and 100 degrees Celsius, water exists as a liquid that is ready to vaporize. Okay, so at exactly at 100 degrees Celsius, okay, this is very precise, okay, because this is ideal case. At exactly 100 degrees Celsius, we assume that the water is in a saturated liquid phase. So once it reach maybe 101 degree or 102 degrees Celsius, then it is no longer at the saturated liquid phase. Maybe still, okay, plus minus, okay, but more than that, is no more saturated liquid. Okay. Next, saturated vapor. Okay, a vapor that is about to condense, condensasi kan, condensation. Okay. So condensation, you understand? Okay, it's okay. First, vaporization. Vaporization is from liquid to gas. Okay, that one I think you already know. And then condensation is the opposite, from gas to liquid, kan? Okay. So a vapor that is about to condense, just about to start to condense. At that point, we call the phase of the water is in saturated vapor. Okay. And then we have saturated liquid vapor mixture. Okay, the state at which the liquid and vapor phase coexist in equilibrium. Okay, this is the moment where the substance, okay, the water, the substance, it has a mixture of liquid and vapor. Maybe for example, before the vaporization just now, okay, after the saturated liquid, okay, at first compressed liquid and then saturated liquid, and then after the saturated liquid, the water will go the vaporization process, right? Okay, during that vaporization process, the phase of the water is a combined, a mixture of liquid and vapor. Maybe at the beginning, after maybe at 120 degrees Celsius, or one too much. Around 101, 102 degrees Celsius. The composition of the water, maybe 80% still liquid at the beginning of the vaporization, and 20% is in gas. Okay, it's already a vapor, means it's already the water is already been vaporized. So at that moment of the vaporization, the phase of the water is a combined mixture of liquid and vapor, saturated liquid vapor mixture. Okay, so the same as in during the condensation process, the opposite, when vapor change to liquid. Okay, so we have that saturated liquid vapor mixture. There's always a percentage of those phase, liquid and vapor. Maybe 80% liquid, vapor 30%, and then it will change until 100%. Saturated means 100%, for example, saturated vapor, 100% vapor, saturated liquid, 100% liquid. Okay. And then superheated vapor, a vapor that is not about to condense, not a saturated vapor, means like just now saturated liquid, subcool liquid or compressed liquid, the temperature is really below 100 degrees Celsius. And now superheated vapor, we assume that the vapor for water, okay, the vapor is not about to condense soon. Okay, so as more heat is transferred, the temperature of the vapor start to rise, so we call this phase is a superheated vapor. Okay, this one. Okay, so for water, maybe 300 degrees Celsius is what we call superheated. Okay, maybe for other liquid, for other substance, fluid, is the temperature change different, depends on the fluid. Okay. Okay, so those are the definitions. So you have to remember that saturated liquid, vapor mixture, saturated vapor, superheated vapor. Okay, because later on, usually in thermodynamics, we have what we call thermodynamics tables. There's a few tables that we use, that scientists use to when you want to calculate the energy balance. So we have to measure the properties, the energy, etc., at each location, at each state of the fluid. So in order to identify the location, the state, okay, of the fluid, we have to know where the phase that the liquid are, the substance are in at those states. Okay, so maybe state one just now, compressed liquid, so we have to look at the thermodynamic tables just for the compressed liquid. Okay, so that one we will see in the example later on. Okay, this one, the diagram, TV diagram. If the entire process between state 1 and 5 described in the figure is reversed by cooling the water while maintaining the pressure at the same value, the water will go back to state 1, retracing. Okay. The amount of heat released will exactly match the amount of heat added during the heating process. Okay. Okay, so this is the diagram. Okay, so in thermodynamics, there's a lot of table, there's a lot of diagram. Okay. So we will use this diagram to illustrate the process, okay, the thermodynamic process. Okay, so for example, this one, okay, the first diagram here, we see TV diagram. So T, temperature, and V is what? V is volume, okay, not velocity, okay, volume. Okay, volume, but here, since it is written as small v, so we consider this volume is in terms of mass per kilogram. Okay, so it's maybe meter cube per kilogram. Okay, so because it is small v. Okay, so example for the water just now, TV diagram for the heating process of water at constant pressure. Okay, another thing. Okay, in the TV diagram or in whatever thermodynamic diagram, other than the parameter, the parameter at the y and x axis, T and V here, there's also other parameters defined in the diagram. Okay, so apa tadi? For example, this one, we have this constant pressure line. Or what we call constant pressure. Constant pressure kita panggil apa ya? In the first week of the class, I've introduced this definition. So maybe I can ask someone just the definition of the constant pressure. Apa nak panggil? Amirul Akmal. Amirul Akmal di situ?
Yes, Doctor.
Okay, constant pressure, what is the name of the constant pressure? Macam mana cakap? Dia adalah nama dia. Apa?
I forgot. Doktor.
Google. Apa kata Google?
Forgot about it.
Forgot. Itu Google.
I thought to Google.
At least jujur lah. Okay, tak apa. Okay, constant pressure tak ingat? Something start with I.
Uh,
No idea?
no idea, Doktor.
Okay, tak apa. Next, Zainul Arifin. Constant pressure. What is the name in thermodynamics we call for constant pressure? There's also other names for constant volume, constant temperature. There are names that we are for them.
Constant pressure is an isobaric process.
Okay, thank you very much. Okay, isobaric or isobar. Okay, thank you. Okay, so constant pressure isobar. So this in the TV diagram we also have isobar lines. Okay, so sometimes so this isobar line change with different substance. For example, this TV diagram. Okay, so one diagram is valid for one substance. So for example, this diagram in this figure here is the TV diagram for water, only for water. If you have oil or the carbon dioxide, so there's another other diagram, a TV diagram for just carbon dioxide. So it's just specific for that substance fluid. Okay, so for example, remember maybe like this one. Ini something like that. So in the diagram, here in this figure, we don't show all the isobar lines because it only shows one line that concern us, which is equals to 1 atmosphere pressure. So, but in the actual diagram, there are several isobar lines exist. Okay, so maybe this one is 2 atmosphere, this one is 3, and this one maybe less 0.5 atmosphere, so something like that. So means that throughout those lines, okay, the water, we assume that the water is in the same atmosphere. For example, if at state 5 and at state 2, okay, even though vertically or horizontally the location, the position change, but the pressure remain the same because it is on the isobar line. Okay, so the pressure for at state 5 is 1 atmosphere, and also the pressure at state 2 also 1 atmosphere, but the temperature and the volume at those state 2 and 5 are different. Okay, so that's why you have to learn how to read the diagram. Okay, so this one is simple. So for water, so imagine just now we start with a state 1. So this process from state 1 to state 5 is what we call vaporization. Okay, so so we start with state 1 where at 20 degrees Celsius just now and at a certain amount of volume. Okay, so the water is in a compressed liquid phase. Okay, so it reached state 2 at around 100 degrees Celsius. So at this point, it is at saturated liquid. Okay, at that exact point, state 2. Once it reaches state 2 and then goes along the line to state 3 and 4. So this is where vaporization process occur. Vaporization. Okay, penguapan. Vaporize from state 2 to 3 and until 4. Okay. So that is a saturated mixture. That is what we call saturated liquid vapor phase. And then state 4 is the saturated vapor. Okay, when it has finished vaporization process. Okay, so we assume that in ideal case, we assume that the process of the vaporization and the process of the opposite, which is condensation, occurs in the constant pressure and constant temperature. Okay, but it's actually in the reality, tak constant macam tu lah, exactly. There's always a bit of the energy loss or pressure loss along the way. Okay, so the temperature and pressure might change a bit, not exactly maintain at 100 degrees Celsius. Ni ideal lah. Okay. So during that process vaporization, for ideal case, we assume that the temperature is at exactly 100 degrees Celsius and the pressure of the water is at 1 atmosphere. Okay. And then when once it reach saturated vapor at state 4, point 4, then the liquid, if the water continue to be heated, continue to be vaporized, then the water will change it phase into superheated vapor. Dia panas lah, makin panas lagi. Kalau kita if we keep give heat to the water, if we stop giving heat, then it will stop and start process of condensation. Okay, so it depends. Okay, so if we keep giving heat up the water, so it will continue to superheated water until superheated vapor until 0.5. Okay, and then if the process is reverse condensation, so by cooling the water, okay, we lower the temperature, so the process will return back to liquid, from the vapor to liquid. Okay, so this is example of a vaporization process at constant pressure. Okay, what else? Saturation temperature and saturation pressure. Okay, the temperature at which water starts boiling depends on the pressure. Okay, we can see just now from the diagram, TV diagram just now, the temperature and pressure depends on each other. Okay, link with each other. If temperature increase, then usually pressure increase. Okay, and vice versa. Therefore, if the pressure is fixed, so is the boiling temperature. Okay, so if we just now, the diagram just now, if the pressure is fixed as 1 atmosphere, so we assume also that the boiling temperature, which is at 100 degrees Celsius, is constant, maintained at that temperature. Saturation temperature, the temperature at which a pure substance change phase at a given pressure. Saturation pressure, the pressure at which a pure substance change phase at a given temperature. Okay. Saya nak explain. Okay. Okay. For this one, usually I'll use another diagram. But yeah, okay. It's okay. Saturation temperature and saturation pressure is like the saturation, kan? Definition of the saturation is like maximum or at the peak point. Okay, so what we mean by the saturation temperature, for example, and pressure also means once we reach that point, okay, is like the maximum level of the liquid vapor phase. Okay. Okay, later on, you look at the there's another diagram, TS. Okay, this is entropy. But okay, I just would like to show you the phase change. Okay. In this another diagram, TS diagram, entropy and temperature, we have this liquid vapor, means a mixture of liquid and vapor, and this is a vapor phase. Okay, so the vaporization, okay, occur. Okay, this is at the peak point here is where the temperature is at is saturated, and the pressure is also at the saturation value. So means that once the temperature and the pressure decrease, lower, then the process of the water will start to become vapor. We start to change to saturated vapor. Okay. So for now, you just understand that saturation temperature and saturation pressure is the kind of the maximum of the value of temperature and pressure for that the the water or the substance can in the water, and that the water will reach. Okay. Okay, so saturation boiling pressure of water at various temperature. Okay, so depends on the temperature. The saturation pressure of the water is different. Okay, tak. Okay, this one tak apa, nanti in the later example application. I hope you will understand better when we look at the application. Okay, just understand first the definition. Okay, latent heat of fusion, latent heat of vaporization. Okay, the amount of energy absorbed or released during a phase change process. Okay, so during the vaporization or condensation just now, the amount of energy, there must be amount of energy absorbed or released, because, for example, for vaporization, we need to heat up the water or the fluid, air or oil, example. Okay, so we need to heat up. So when we heat the fluid, means that we give energy. Okay, there's amount of energy that is going to be absorbed or released. So this amount of energy from heat, okay, is what we call latent heat. Okay, so the latent heat of fusion is during melting. Okay, which is equivalent to freezing, the opposite of the melting, freezing. Okay, and latent heat of vaporization is the amount of energy absorbed during vaporization, which is also assumed to be equivalent to the opposite, which is condensation. Okay. Okay, so there is amount of energy. So energy, usually we use a joule. Okay, kilojoule or joule. Okay, depends on the temperature or pressure at one. Okay, for water, the latent heat of fusion is 333, and for vaporization 2256. Okay. Those are the value. You don't have to remember the values, just for your knowledge. Okay. Okay. For example, this one, okay, related to maybe aircraft. Okay. Okay. So at different pressure, at different atmospheric pressure. Okay. At different elevation, altitude. Okay. Different altitude. So the water or air have a different atmospheric pressure. So of course, the boiling temperature, the vaporization temperature also will change, depends on the pressure, atmospheric pressure or elevation. Okay, due to the ketinggian, altitude. Okay, so some consequence of saturation and saturation temperature and temperature and saturation pressure. Okay, so here, from here, for example, water or nitrogen. Okay, so once we know the saturation pressure and vapor pressure and temperature, okay, so we know at what point the substance, nitrogen, water, will start to cool or to vaporize. Okay, so it is an important indicator, okay, for us, so that we know until at what temperature we need to manipulate, okay, to handle the substance. Okay, so ini penting lah untuk kita tahu saturation temperature dia bila apa semua, so kita tahu bila dia akan berlaku cooling, bila akan berlaku vaporize semua. Okay. Property diagrams for phase change process. This one is the one that I draw just now. Okay, so this is the isobar line that I talked about just now. Okay, the variation of properties during phase change process are best studied and understood with the help of property diagrams. Okay, so this one is TV diagram. So there's a lot of other diagram, PV diagram, PT diagram, etc. Okay, so this is TV diagram for water. Okay, so just now that we've seen for pressure 1 megapascal, 1 atmosphere, 10 atmosphere. Okay. Okay, so those are the pink line, the isobar line. So along that line, the pressure is assumed to be constant for isobar. Okay, so okay, critical point. Okay, critical point. So the the diagram that I sketched just now, this is the critical point name dia. Okay, that at this critical point that the pressure and temperature reach the saturation value. Okay, so the same thing for TV diagram here. Okay, so each isobar line, it has the critical point. Okay, so this critical point is what we call at this critical point is the saturated temperature and pressure. So for example, for this one, okay, for this line at pressure 22.06 megapascal, okay, 22.6 megapascal, the critical point is here. Okay, so means that the saturated temperature at this pressure for this water is 373.95 degrees Celsius. So this is the saturated point. Okay, so once after that line, after that point, the water, okay, along this line, okay, will start to change phase, will start to become vapor slowly. Okay, the vaporization process will begin, but before the saturated temperature, we assume that the water is in a compressed liquid phase. Okay, so ni this one along this line, it is in liquid. Once it reach here, it start to vaporize. Okay, so for other pressure 0.1 megapascal or 0.01 megapascal, the critical point is different. Okay, so it depends on the pressure. Okay, so we also have saturated vapor here. Okay, TV diagram of concentration phase change. Okay, so that is saturation diagram, phase change process. Lagi okay, the same thing here. This one. This okay, this one and this one here on the right hand side. For example, P1, the line dot line P1. I'm not sure. Okay, maybe 1 megapascal here. Okay, so the vaporization process will begin from here. Okay, saturated liquid, and then here in here is liquid plus vapor. This one is liquid and this one is vapor. Okay, so I always write that way. L liquid and L plus V is mixture of liquid and vapor, and V is vapor. Okay, so along this line until it reach the critical point, this line, okay, this line is the saturated liquid line. Means that if the water is the state of the water is along that line, we assume that the water is in saturated liquid phase. Okay. Sekejap. Padam balik. Okay, macam mana? Okay, means that, okay, for example, if the water is at 20 degrees Celsius, okay, at 20 degrees Celsius, so 20 degree, okay, at 20 degrees Celsius, the water will reach saturated liquid at pressure, for example, is P1 is 1 megapascal, so at this line, it should be lower, maybe around 0.8 megapascal. Okay, so means that at 20 degrees Celsius, the temperature, the pressure for saturated liquid is 0.8 megapascal. Example, kat sini here it doesn't indicate. I didn't indicate the value of the pressure, so I just put whatever value. Okay, 0. So at 20 degrees Celsius, the saturated liquid means the liquid will start to vaporize at 0.8 megapascal. Okay, But if you have the water at for example 50 degrees Celsius, example okay, so the saturated liquid point will be maybe around 1.2 megapascal. Okay, so at 50 degrees Celsius, saturated liquid at 1.2 megapascal. So it changed. Okay, it's changed depends on with temperature and pressure. Okay, saturated liquid. Okay, critical point, the point at which the saturated liquid and saturated vapor states are identical. So at this point, we have both saturated liquid and saturated vapor. Okay, but along this line, only saturated liquid, and along this line, only saturated vapor. Okay. Okay, at supercritical pressure, P higher than P critical, PCR is critical. There is no distinct phase change boiling. So supercritical is means that if the pressure is higher than this point. For example, if this point for water, critical pressure for water, I don't remember it. Okay, critical pressure, so I just put maybe 10 megapascal, example je. Okay, so if the pressure of the water is higher than 10 megapascal, maybe 11 megapascal, so we said that the water is in supercritical phase. Okay. Okay, so at supercritical phase, the pressure and the temperature will be very, very high. Okay. So, okay, the same thing. Okay, this is, just now, this is TV diagram. Even though it looks quite same, but it's different. This is TV diagram. So we have isobar line. But for PV diagram, pressure V volume diagram, P, okay, look at the y-axis vertical line. Okay, for PV diagram, we have this constant temperature line. So what is the name for this constant temperature? Maybe Miza Shazwina.
Yes, doctor.
Apa nama yang untuk yang temperature pula, constant temperature? Tadi isobar kan untuk pressure.
Constant.
Iso ada sama je, iso juga. Lagi mudah.
Isothermal.
Okay, thank you. Isothermal. Okay, so this is the easiest. Another one for volume constant volume is isochoric, but we seldom use it. Okay, but we use more often the isobar and isothermal term. Okay, you have to remember that. So constant pressure line, constant temperature line is what we call isothermal. So the isothermal line in PV diagram is like this. Okay, ni the dot line. Okay, so along that line, we assume that the temperature is constant. So you have to know how to read the diagram. Okay, so means that if you have the water at this state or at this state, the temperature will be the same, but the pressure and volume is different. Okay. Okay, the pressure tak apa. Okay, extending the diagrams to include the solid phase. Okay. Just now, what we have seen only liquid and vapor phase. So there's another one which is solid. Okay, maybe for aerothermodynamics, aircraft engine, we focus more on water and on fluid lah. Fluid is vapor and liquid, both liquid and vapor. What is what we call fluid. Solid is for solid mechanic. Okay, but we still have to learn about this. Okay, so PV diagram, the diagram just now is it actually can be extended, okay, with solid liquid and solid vapor line. Okay, so we also have solid liquid, solid vapor, like you see in this diagram, solid vapor, solid liquid. Okay, because solid liquid, from solid to liquid is the like the melting process. Okay, and the opposite is freezing, right? Liquid to solid. And then we have solid and vapor also. Okay, so tak apa. Okay, solid we seldom use in this aerothermo. Okay, this is the triple point temperature and pressure of various substance. Okay, triple point. Okay, this one, the triple line. Okay, means at this line, we consider that the substance is in three three saturated phase: solid, vapor, and liquid. Okay, but we seldom use it. We only focus on this critical point. Okay, liquid and vapor. Okay, tak apa. Sublimation for solid and vapor. Okay, the triple point here. Okay, sublimation. The process a change from solid to vapor is what we call solid evaporate without melting first, sublimation. Okay, so this one kita apa? Okay, we also have this the diagram in 3D. So what we call PVT diagram: pressure, volume, temperature. Okay, so sometimes we use this 3D three dimension diagram also, but it's the same. Okay, just like for example just now PV diagram, you only pick this part and illustrate it in sketch it in 2D diagram 2D axis to axis. Okay, so it's the same diagram. It's just that this is in 3D with three different parameters: pressure, volume, and temperature. Okay, so we know that at this point, the substance is in liquid. After this point, the substance is in vapor, and above vapor, we have gas or superheated vapor. Okay, this is more interesting. Okay, after you know the definition of the process, those process, those different phase. Okay, liquid, vapor, solid. Okay, we will take a break at 10:15 later on. Okay, property tables. Okay. Okay, so I'm going to introduce this one physical parameter. Okay, which is very important in to calculate energy balance, to measure anything. The first law of thermodynamics. So this is what we call enthalpy. Okay, enthalpy is noted as H. The symbol is H. Enthalpy. Okay, so it can be in terms of mass, kilojoule per kilogram, or just kilojoule. Okay, but usually we will use in terms of mass, kilojoule per kilogram. Okay, or joule per kilogram. So this is enthalpy. So what is enthalpy? Enthalpy is the combination of U plus PV is frequently encountered in the analysis of control volume. Okay, U plus PV. Okay, U is internal energy. Ada two definition. Internal energy means that the energy inside the substance. Okay, internal. So it always relates with temperature, pressure. Okay, this is what we call internal energy. And we have H. H is enthalpy. Enthalpy. Okay, the product pressure volume has energy unit. So this is PV, also energy. This one is also energy, joule, and this one is energy, enthalpy. Okay, so when we want to measure the energy balance of a system, of a control volume, so it means that we have to calculate the enthalpy. Okay, in a compressor, turbine, right? We measure the energy balance within those device by using enthalpy. Okay, because it is in energy measurement, which is in joule. Okay, the standard the SI unit for energy. Okay, so we have U in U out. Okay, from control volume, and then saturated liquid, saturated vapor state. Okay, this is how you read the one of the thermodynamic table. Okay, so like I mentioned just now, in thermodynamics we have several diagrams, thermodynamic diagrams, and we also have tables. Okay, so the values, the thermodynamic values from the diagram just now, it is also being tabulated. Tabulated table lah, in a table. Okay, so is from the same diagram, from the same PV diagram, TV diagram, apa lagi tadi, PT diagram just now. Okay, we can scientists, they tabulate those the values in a table, and we can use this table for our own calculation. Okay. Okay, so A4, A5 ni actually because I'm using this reference thermodynamics books that I've mentioned, thermodynamics McGraw-Hill. Okay, so at the appendix of the at the end of the book, reference book, it has it has these thermodynamic tables. Okay, that it names as A4, A5, A1. So that's why A4, we use this table A4, A5. Okay. Okay. So table A4 is saturation properties. If you have that book, or you have the, I'm not sure if they have the PDF. But at our library, this book exists. Okay. You can borrow. Okay. So table A4 from the appendix is saturation properties of water under temperature. Because and table A5 is saturation properties of water under pressure. So there are two types of table given here in this book. Table A4 and 5 depends on the temperature or pressure. Okay. So one for A4, it gives you the values in terms of saturation, in terms of temperature. Means you have to know first the values of the temperature, then you can read at this temperature. For example, at 85, the saturation pressure is 57, the saturation liquid, the specific volume, okay, the volume, the V is 0.001, and then 2.8. Okay, so you can read the table. Okay, so for table A5, under pressure means that we have the values of the pressure, and then it will give you the value of the saturation, saturated temperature. Okay, boleh kot saya tunjuk yang ni. Okay, sekejap wait. Maybe I can okay, can you see my screen? Okay. So you know the you can also just Google. I think there's a lot of the in Google the table you can search for yourself. Okay. So this one, the saturated water. Okay. This is so we have the value of the pressure. We have the value of the pressure 1 kilopascal. Okay, it's in kilopascal. So be careful. Okay, so this 1 atmosphere, 1 megapascal here. At 101.325, this is the value of 1 atmosphere. So we can read. So if we have water at 1 atmosphere, and so we know this that the saturated temperature of the water at this 1 atmosphere is 99.97, which is nearly 100 degrees Celsius, like we mentioned just now. Okay, so the value of the specific volume is this. The internal energy U is this. Okay, enthalpy. So we have the value of the enthalpy H. Okay, so at 1 atmosphere atmospheric pressure around 100 degree or 99.997. In your calculation, you have to use the exact value. Okay, don't round it. Okay. Jangan bundarkan ke 100 pula. Sebab kita ada yang ni, kita guna yang ni. Okay. And then, so we know that the enthalpy at the saturated liquid, okay, is 419.06. Okay. But during evaporation process, the mixture of liquid and vapor, the enthalpy is 2256. Okay, so be careful. You have to, that's why you have to understand you have to learn how to read the table. Okay, you have to read the table, so you have to pick the correct value. If we ask you the saturated vapors, then you have to change, as you have to pick this enthalpy. Okay, entropy is the second law, so we will learn this second part after the mid-sem break. Okay, so we focus first on the specific volume V, internal energy kilojoule per kilogram, U, sorry, and enthalpy H. Okay, so you can see here each of these values, internal energy, enthalpy, it has three different measurement. Okay, three different values for different phase. So that's why just now we have to learn first about the pure substance and the definition of this different phase, because then we have to apply this. Okay, when we read the table, or when we look at the diagram, so we know which one that we have to pick. So you have to understand the process. Okay, make sure that. Okay, so back to the stop presenting. Okay. Okay. Kita balik. Mana tadi? Okay. Okay. So you can just Google the those tables, saturation properties. Okay. So VF with the small f is specific volume for liquid, and just now if H is the enthalpy of saturated liquid. Okay, Vg is a specific volume of saturated vapor. Vfg is the difference between Vg and Vf. That is okay. So is where the phase, the water is in both liquid and vapor phase. Okay. Enthalpy of vaporization, latent heat of vaporization just now. Okay, the latent heat that I mentioned just now. So that is the amount of energy needed to vaporize. So we have that value in the table also. Okay. Okay. Okay, this one sama je tadi. Okay. So maybe I show this one. So in the diagram, for you to understand better, when you read the value, so at which point those values are located in the diagram. So for example, this one. Okay, so this one, so at 100 kilopascal. Okay, so this point, saturated liquid. Okay, saturated liquid. So we can read its VF. Okay, the specific volume at saturated liquid. So what we read here, what we are reading here, okay, is the VF at the saturated liquid. Okay, in the diagram here. Okay, so that is what it means. Okay, so Vg is the specific volume for saturated vapor. Okay. Okay. This one is the saturated liquid vapor mixture. This notation. Okay. We introduce this notation X, or what we call quality. Okay, quality is X. Okay, the symbol is X. So it's like the tapi bukan efficiency lah, percentage. Okay, the ratio of the mass of vapor to the total mass of the mixture. Quality is between 0 and 1, so it is always between 0 and 1. Okay, so that's why I call it like a percentage. Okay, so at 0 it is the saturated liquid, and at 1, if the quality is at 1, means that the substance is in saturated vapor phase. Okay, so the properties of the saturated liquid are the same whether it exists alone or in a mixture with saturated vapor. Okay, so for example, so the ratio X is the mass of the vapor over the mass of the total substance at that time. Okay, so that's how we get the quality or the percentage of the vapor inside the mixture. Okay, so that's why during the vaporization process or condensation process, we always given the quality of X. For example, if we have during that vaporization process, we have X example 0.2. Okay, we have 0.2 X during that vaporization process. So it is given X equal to 0.2. So when X is 0.2, means closer to value of 0, so we can imagine that the vaporization process is maybe just started. Okay, because in the mixture it only has 20% of vapor, means the rest 80% is the mixture is still in liquid form, liquid phase. Okay, so that is what quality X means. Okay, so maybe towards the end of the vaporization process, we have 0.9, 0.8 X quality, means that the mixture, the water, the mixture, uh, 90% or 80% is in vapor phase, and only 10 or 20% is still in liquid that need to be vaporized. Okay, so that is quality. Okay, so we can use this quality X values, properties, okay, to calculate the internal energy U or enthalpy average. Okay, so those are the equation, and the specific volume also we can use X. Okay, so if we know X, okay, we know the quality, so we know okay. Actually. Okay, for example, this one. Okay, we want to calculate the internal internal energy or H enthalpy at this point. Okay, so we know the quality. Maybe here around is still close to saturated liquid, so maybe around 0.4 at 0.4. Okay, so we can look at the table just now, the thermodynamic table, table A.4 or A.5. Okay, so we look at at this at this point, the pressure and temperature. Okay, we can look at the table and search for the UF or HF and UFG or HFG for at that pressure or temperature value. So from this value, and then we can calculate the U average at this location at this point. Okay, because this one we can get from the table, and we know X, so we can use that to measure the enthalpy, the specific volume, the internal energy at that point. Okay, during the vaporization or condensation process. Okay, superheated vapor also the same. Okay, superheated vapor means after the saturation vapor. Okay, boleh lah. Okay. So we have also tables. Okay, compared to saturated vapor, superheated vapor is characterized by lower pressure. Okay, at a given T. Okay, so for example, if the saturated vapor is at this point, so the superheated vapor can be lower than the pressure of the saturated pressure here. Okay, at a given temperature T, higher temperature. Okay, at a given P. Okay, because if the superheated vapor is at this point, okay, superheated vapor at this point, so the temperature for superheated vapor is higher than the temperature at the this. Okay, higher specific volume V here and V here, high internal energy, high enthalpies. Okay, so this is what we expect from superheated vapor. If we continue to heat up the vapor, the vapor continue to boil, then we expect that this value, temperature, specific volume, U and H enthalpy will increase. Okay, so if we want to achieve a higher internal energy or higher enthalpy, higher energy, then we need to increase more to heat up more the vapor. Okay. So compressed liquid is the opposite of the saturated vapor just now. So the pressure will be higher. Okay. Temperature will be lower. Okay, sebab dia line kat sini the isobar line. Okay. So it is the opposite of the saturated vapor just now. A more accurate relation for H. Okay. Okay. Kita tengok. Okay, reference state and reference values. Okay, so these are the tables. Okay, table A4, A5 just now. So the values of U, H, and S cannot be measured directly. They are calculated from measurable properties using the relation between properties. Okay, okay, so we have this one, table 8.4. For example, if you have temperature, okay, the first table is water, and the second table is refrigerant 134A. Okay, so it's different. So the table, the thermodynamic tables is specific, unique for each substance. So different substance, carbon dioxide or refrigerant, different refrigerant, it has to have another different table. So we cannot use the same table for different fluid or different substance. Okay, so that's why we have to read carefully. Okay, the title. Okay, the name of the table. So if you search later on, if you search or you want to search for this table, so make sure you read carefully. The table is about what, water or refrigerant or any other fluid. Okay, so because you will have different values. Okay, so for water at temperature 0.01, pressure 0.6, so you have specific volume. So you can read along this horizontal line. Okay, this volume, this value. Okay, and saturated vapor, temperature minus 40 degrees Celsius. Okay, so we have all these given values. So you can use to calculate anything, to calculate enthalpy or internal energy average just now. Okay, before ni topik lain pula. Okay, so before we continue, I think we can take a small break. Okay, ada yang baru enter, tapi kita dah start, we have started at 9 a.m. Okay, I repeat again, our class is at 9 a.m. to 12 p.m. not 10 a.m. Okay, I have changed it. Okay, so now we take a break, maybe 10 to 15 minutes until 10:30 lah. Okay lah, 10:30. Okay, so we come back in 15 minutes. Okay. Okay. Everyone is here? Can we continue? Al-Mansur Omar, are you here? Mutaman?
Yes, Doctor.
Semua dia kena panggil nama. Abdullah Syed Hamdan. Okay. Al-Mansur
Yes,
Omar. Okay.
You said my name, but
Okay. Sekarang kita ada how many? 12. There's still two. Ada two students who are not who didn't attend. I'm not sure that I tengok. Wait, down pula SMP. SMP tak lupa. Tak apa. Okay. Okay, it's okay. We continue first. Okay. Okay, so after the property tables, the thermodynamic tables, the pure substance diagram, etc. Okay, so now what is it here? Property tables provide very accurate information. Property tables means the thermodynamic table just now, but they are bulky and vulnerable to typographical errors. Okay. Of course, there are some errors. It could be some errors in the those properties tables. So there are a more practical and desirable approach need to be done. Okay. So what we have, one of the most important part also in thermodynamics is the ideal gas equation of state. Okay. Okay. The gas equation of state. Equation of state, any equation that relates the pressure, temperature, and specific volume. Okay, so for ideal gas, ideal gas, it doesn't mean only air. It can be any other substance, gas, helium, argon, nitrogen, carbon dioxide, etc. As long as it is in ideal gas state. Okay, so normally for ideal process, we try to assume first that the process or the substance, the gas is in ideal state, the ideal gas equation of state, so that we can apply this equation of state. Okay, so this equation of state of ideal gas links the volume, pressure, and temperature, and another parameter which is called gas constant, or sometimes it is called universal gas constant, RU. Okay, but usually we will use the first one, gas constant R, because it is in joule or kilojoule per kilogram per Kelvin. It is in SI units. Okay, so this equation of state is very simple. It's PV equals to RT. PV, the specific volume, in terms of mass, RT. Or sometimes if the V is the big V, okay, we can also write it this way. Okay, if you have the volume just in meter cube, okay, and so we must include the mass in kilogram. Okay, so the equation of state will become PV equals to MRT, the mass RT. Otherwise, if we have the specific volume, V over M mass, so we can write we can use the specific volume V, small v. So this is the ideal gas equation of state. Okay, so R, for example, the gas constant R for air, because we will use this R more frequently in for aircraft aerothermo. So R is 287 kilojoule per kilogram Kelvin. Okay, R is 287 kilojoule per kilogram per Kelvin. Okay, this one 0.287. This one kilo, yang ni in joule. Joule per kilogram Kelvin 287, but in kilojoule is 0.287. Okay, for air, you have to kind of like remember this video because you will use it several times often. Okay. But usually I will give this video and you can also search for it. Okay, mass. Okay, molar mass times mole number. Okay, if we have a mole number, we can also write all those parameters, the specific volume, internal energy, enthalpy, in terms of per unit mole. Okay, per unit mass of per unit mole. So if you use per unit mole, you have to have like the bar above the parameter, the physical parameter properties. Okay, so it's kilojoule per kilomole or meter cube per kilomole. Okay, but we use more frequently the per unit mass, kilomole. Maybe in chemistry, they use in per kilomole, but us for in mechanical or aerospace, we usually use in per unit mass. Okay, so those are the equation to change it from kilogram to kilomole. Okay, ideal gas equation at two state for a fixed mass. Okay, so we can also apply this equation of states. This ideal gas equation at two different states, state 1 and state 2. Okay. So we assume that the mass is fixed, M1 the conservation of mass. So here, conservation of mass, remember, first week, I already tell you about this. It's a conservation of mass. Okay, M1 equals to M2. Just now, so we have here M, the equation of state PV over RT, right? So M1 P1 V1 RT1 and M2 P2 V2 over RT2. Okay, so that's why from here we get this. Okay, so R is constant. Doesn't matter M1 or M2, M3, etc. R is always the same value for the same substance. So R can be eliminated. So we have P1 V1 over T1 equals to P2 V2 over T2. Okay. Tak apalah. Okay, I skip this one. Compressibility factor. Okay, compressibility factor is what we call Z, a factor that accounts for the deviation of real gas from ideal gas behavior. Okay, of course, in reality, we seldom have gas in ideal gas state. Usually, it is a real gas state. So, how much the gas is deviated from ideal gas concept properties? So this deviation is accounted by using this factor Z. Okay, so Z may be more than 1 or less than 1. Okay, so if we have Z equals to 1, it is a ideal gas. We assume that the gas is in ideal gas state. Okay. So for Z also, we have this diagram, Z versus the pressure, reduced pressure. So we can use this diagram here on the left hand side. Okay, so if we have the value of Z, so we can search, okay, for each of these substance, methane, ethylene, ethane, propane, etc., butane, etc. We can use this diagram to search for its temperature and pressure. Okay, so we can apply this Z diagram. Kita jangan guna, but we seldom use this, so that's why I go a bit faster. Okay, other equation of state. Okay, other equation of state, there exists also other equation of state that we call van der Waals equation of state, and another one Beatty-Bridgman. Beatty-Bridgman equation of state. Okay, so this van der Waals, Beatty-Bridgman, so there is Benedict, Redlich, etc., can be used also, okay, to for the equation of state of gas, okay, because the ideal gas equation state just now PV equals to RT is very simplified. It's quite simplified. Okay, so sometimes it neglige it eliminates or it neglige certain factors. Okay, so sometimes the measurement, the calculation is not very really accurate. Okay, but it is enough, sufficient for to calculate any process that can be simplified in ideal case. Okay, so van der Waals, we can also use this one. It is longer, it's a bit more complicated. Okay, the equation of state. Okay, because it is more precise. Okay, in terms of reality. Okay. BT Bridgman Benedict viral equation of state. So ada banyak lagi lah. Okay, tak apa. Ni skip. Okay, specific heat. Specific heat is an intensive property, SI unit, kilojoule per kilogram per Kelvin. Okay. Okay, specific. Mana nak mula ni? I use this one lah. Okay. Okay, this specific heat, it is usually in terms of joule per kilogram per Kelvin. So means that specific heat, we measure the amount of energy in joule that need to be given to the fluid or to the substance in order to increase its temperature, the substance temperature, 1 degree Celsius or 1 Kelvin per unit mass. Okay, panjang. Okay. For example, C at constant pressure, we have for okay, for air, the value is 1005 joule per kilogram Kelvin. This is also a constant parameter other than R. Joule per kilogram Kelvin. Okay, so specific heat, it measure the energy, the amount of energy that need to be given to the substance in order to increase 1 kilogram of mass of the substance to per Kelvin or per degree Celsius. Okay. Okay, we focus on two types of specific heat. So there are two types of specific heat. Constant volume process, another one for constant pressure. So this one is constant pressure. Oops, constant pressure. And this one constant volume. Constant volume, we write it as CV. Okay, so depends. So that's why we have to know first whether the process is at constant volume or constant pressure. Okay, then we can choose which specific heat to use, because the value of the specific heat is different. Even though the same substance, for example, water or air. Okay, here air. CP is 1005, but the CV for air at constant volume is different. Okay, so that's why we have to know first constant volume, whether the process is constant, is considered as isochoric constant volume or isobar constant pressure. So from first law of thermodynamics, okay, I remember this one is the first law of thermodynamics. Okay, so for constant volume, usually we use internal energy U. Okay, so if the okay, W, this one, the differential of W, the work, W is work, okay. Q is heat transfer, W is work done by the systems, and U is the internal energy. So this is part of the first law of thermodynamics. First law of thermodynamics is about energy balance. Okay, remember that first law of thermodynamics, energy balance. Okay, but we will see again in next chapter, chapter 4, 5. Okay. So I just want to explain this equation. Work, the differential form of work, okay, or dW, okay, the derivation. So this is usually written integral P dV, the equation for work. Okay, work is P dV. Okay, just now, yang slides. Mana tadi? Slides yang ada. This one. Bukan. Yang ada PV tu. This one. Okay. So actually it's the same. Okay. This enthalpy equation. Okay, H here is V. Is Q, sorry. The Q. Okay. Okay, H, enthalpy is the include all the energy formed in the system. So it can be heat transfer, Q, kinetic energy, potential energy, etc. Also included in this all enthalpy. So this is also first law of thermodynamics. So don't be confused. So sometimes when I mention first law of thermodynamics, then I use this enthalpy equation, and then sometimes I use the delta Q, delta W just now. It's actually the same. Okay. But this is also first law of thermodynamics. So Q can be part of this H, enthalpy. U is that like delta U just now, and PV, this PV is the work, delta W or dW, the work done. Okay, so that's why from here, okay, so actually this is the same, so don't get confused. So actually, so this is the same. So imagine if the heat transfer is H. So this one is PV. Okay, and U internal energy. Okay, so for constant volume process, since we mentioned constant volume process, so this one, the differential form of dV will be 0. Okay, because constant volume, so no change in volume, so dV 0. So that's why we get this. We cut out the work. Okay, so we only have delta Q equals to du, differential of U. Okay, so du, the internal energy, the definition is this. Okay, specific heat at constant volume multiply with the difference of the temperature change. Okay, the temperature change during the process. So if you have evaporation or vaporization process, okay, at constant, and the process occurs at constant volume. Okay, so you can use this specific heat CV, the value of CV, and we measure the difference of temperature before and after the process, so delta T. So the total of this du is what we call the change in internal energy, and at the same time the total heat transfer be transferred to the process, delta Q heat transfer. So in here, for this specific process, internal energy is equal to the delta Q, total heat transfer. Okay, so CV can also be written as du over dt at V constant. I think right now, since you have learned engineering maths 1 and maths 2, right now you understand this notation. So CV can also be written in this differential form du over dt. Okay, so the differential form of du over dt at constant volume is what we call CV, specific heat. Okay, another one, constant pressure process, CP. Okay, this CP, so the same from first law of thermodynamics. So we have delta Q equals to du plus delta W, or also du plus PDV, because the work done is PDV. Okay. So we can change this form and change it into dH. So delta Q also equals to dH, enthalpy. Okay, and this enthalpy dH can be written in with a constant pressure, specific heat, Cp, and the change in temperature, dT. Okay, change in enthalpy with temperature at constant pressure. So if we have a constant pressure process, we can use this specific heat Cp equation to calculate the change in enthalpy or the energy balance. Okay, the first law of thermodynamics. So dia ada banyak nama, there's a lot of name. Okay, so but the initial root, this equation comes from the first law of thermodynamics. Okay, so that's why this is very important. Okay, you have to understand first about the first law of thermodynamics, the energy balance, because after that, all of the other application, it is derived from this energy balance of first law of thermodynamics concept. Okay. Okay. Okay, internet energy, enthalpy, and specific heat. Okay, from the ideal gas equation just now, we have PVRT. Okay, and then okay, the first law of thermodynamics, H equals to U plus PV. So PV can be written also as RT. So we can replace the PV with RT for ideal gas. Okay, so please make sure. Okay, if you have we can apply this first law of thermodynamics like this only if the fluid is assumed to be ideal gas. Okay, if the fluid is not assumed to be ideal gas equation, then we cannot change it from here to here, from RT from PV to from the first line to the second line. We cannot change to that if the gas is not in ideal gas state. Okay, so please remember that. Okay, this change, this transformation only valid if the gas is in ideal gas equation. So that's why if you read articles, journal papers about thermodynamic process or anything, okay, application, later when you do your final year project, if you choose a project that related to this thermodynamic or propulsion, okay, you must state first what is your hypothesis, what are your assumptions. So one of the important assumption that you need to justify to state first is that we assume throughout the process the gas or the fluid is in ideal gas equation. So once you mention that, then you can apply all these equation. Okay, so you have to mention that first. If you don't mention that, then we assume that it is a real gas. So when it is a real gas, there are some of the equation that it cannot be applied. It is wrong. It means that your research, your experiment is totally wrong, or your assumption is wrong. So you need to justify to clarify that first. So it's very important. So in physics, science, etc., it's very important to clarify first our assumption. Okay, before we proceed with the experiment. Okay, even though our assumption is not true or deviate from different from the truth, but we need to clarify first. Okay, from the specific heat relation, so once we have H equals to U plus RT, and then we know that U is CV dt. Okay, this the specific heat just now. Okay, so we can so we can use this one. We can use this HU plus RT or like H equals to U plus PV. Okay, so sama je. Okay, okay, so this is the one that we have to remember. So delta U or du differential value of U is equal to CV dt or delta T, temperature, or we can also use enthalpy, dH equals to Cp delta T. Okay. Another point is that the relation between Cp and Cv itself. Okay, there's also a relation between this. Cp equals to Cv plus R, the gas constant just now. Okay, Cp, because the unit is the same, specific heat and gas constant use the same unit, joule or kilojoule per kilogram per Kelvin. So there exists a relation between them, okay, which is Cp equals to Cv plus R. Okay, in kilomole as well. And also here, K, the specific heat ratio, K or small k is, or sometimes we use gamma. In the thermodynamic book, sometimes we use gamma. Okay, so K gamma is the same. It's the specific heat ratio. It define the ratio of Cp over Cv. Okay, so for air, okay, for air, gamma, okay, this specific heat ratio equals to 1.4 or sometimes 1.33. Okay, this one we use a lot in propulsion. Okay, this is for ideal gas. Okay, all of this value, one day you will remember it, okay, because we will use a lot of time, especially for air, water. Okay, so gamma, specific heat ratio, or K, is the ratio of Cp over Cv. Okay, finish. Okay, okay, so those are the definition, okay, of this thermodynamics pure substance. Okay, now we will take some time to take a look at the example tutorial. We start with the easy one first. Okay. So exercise 1, a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees Celsius. Determine the pressure in the tank and the volume of the tank. Pressure in the tank and the volume of the tank. Okay, so for this one, you can, I think we have to use the table. Okay. I'm not sure if by this time you dah download ke. Masuk. Sekejap. I think you boleh search, you guys can search and download sekejap. Saya the apa tu, property tables. Kalau guna okay. I try to send at the WhatsApp group. Sekejap. Mana tadi? Yang ni ke kena sekejap. Okay, I send one first. Okay, we take a look at it. Rigid tank contains 50 kilogram saturated liquid water. Okay, the beginning of our chapter just now. Okay, mana tadi? So 90 degrees Celsius. Bukan yang ni, kena guna yang satu lagi ni. We have to use another one. 90 degrees Celsius pressure, saturated liquid water at 90 degrees Celsius. Okay, betul lah. Saturated pressure at temperature 90 degrees Celsius. Betul ke table yang ni? Cuba saya guna. You guys can search for the table. Sekejap saya tengok table saya. 70 ni 90 saturated water. Pressure table. Oh, kena guna yang satu lagi ni. Sorry, not that one. Kena guna saturated water pressure table. That one yang the one that I share is temperature table. Kena tukar. Pressure table. Okay, 75 jap. Satu ya, pressure table. Pressure table. Oh tak, temperature table. Table A4. Boleh kot yang ni. Tadi 70, 90 degrees Celsius. Okay, this one. Saya screenshot yang ni. Okay, the second table that I just sent at the WhatsApp group. Okay. Okay, look at the table. Okay, so a rigid tank contains 50 kilogram of saturated liquid water at 90 degrees Celsius. Okay, so since we know the value of temperature 90 degrees Celsius, so we will use this one. Okay, is stated here saturated liquid water. So we use saturated water table A4. So 90 degrees. So how you read the table? So 90 degrees Celsius, temperature 90 degrees Celsius. So the pressure is 70.183 kilopascal. Nampak? Okay, 70.183 kilopascal. Okay, so this will be the value of the pressure in the tank. Okay, the value of the pressure in the tank. And the volume of the tank. Okay, so in order to calculate the volume of the tank, okay, we can use the value of the specific volume here. Okay, the specific volume is meter cube per kilogram. Okay, and then we have to multiply with the 50 kilogram given. Okay, so back to this line, this row. Okay, 90 degree. 70.183 saturated pressure, and then the liquid because it is stated saturated liquid water. Okay, so you choose this one, not this one. Okay, because it is stated saturated liquid. Okay, so read carefully the example, the questions. Okay, saturated liquid, so 0.001036. Okay. So this is the specific volume, and we know the volume is 50 kilogram, 50. So multiply this one with 50. Okay, so simple je lah. Okay. So back to the question just now. Sekejap saya tukar-tukar device ni. Saya guna yang ni lah. Share the state. Okay. Suka pula. Okay, so the question here, a rigid tank contains 50 kilogram. Okay, so you have search the value in the table just now. Okay, so pressure at the saturated. So read carefully this one. When it said saturated, okay, first water. Okay, water. Mention water. So look up at the table for water. Okay, don't choose other tables for refrigerant or other fluid. Okay, use water, and then mention here liquid. Okay, So liquid, okay. So that's why in here we look up at the specific volume for liquid 0.001036 instead of the saturated vapor. Okay, so don't be confused. Okay, so just that and multiply with 50 kilogram. Okay, so you get the pressure directly from the table and volume, specific volume, and multiply with 50 kilogram. Okay, that's it. Senang je. Okay, next. Of course, we start with easy first. Okay. Next, a mass of 200 gram. A mass of 200 gram of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascal. Determine the volume change. Okay. The volume change and then the amount of energy added to the water. Okay. So for this one, since we have instead the value of pressure, so we have to use the table A5 with the first table that I give in the WhatsApp group for the pressure table. Okay. This one okay, this one is table A5 actually. Apa tadi? A mass of 200 gram of saturated liquid water is completely vaporized, okay, at a constant pressure of 100 kilopascal. Okay, so we read the table. Okay, sekejap dia nak calculate. You want to calculate the volume change, the specific volume, okay. 100 kilopascal. At 100 kilopascal mana ni? Okay. 100 kilopascal. Okay, so we have the specific volume 0.001043 and 1.6941 for saturated vapor. Okay, so the questions, you want to know the volume change. So the volume change is the VFG. Okay, the average volume throughout the process at that time. Okay, so it's not just VF or not just VG, but we want to search for the change of volume. So VFG. Okay, so the change of volume VG minus VF, because always VG is higher than VF. Ada tulis kat sini tadi. Okay, just want to show back the ni tadi tulis. This one, tadi lah. This one. Okay. VFG is VG minus VF. The difference between VG and VF. Okay. So we want to calculate this VFG. So we have to look up at the both of the value VF and VG at 100 kilopascal. Okay. So back to our questions. Okay. So and back to our table. Okay, 100. So we take VG 1.6941 minus VF 0.001043. So we get the VFG, the difference, the average specific volume, not yet volume. Okay, so the volume change, so you have to multiply, don't forget, with the mass given 200 gram. Okay, so 0.2 kilogram. So multiply it, so you get the volume change A. Okay. Easier. Okay. Next one. The second one B. The amount of energy added to the water. Okay. Amount of energy added to the water. So energy. Okay. So it's practically it's we talk about enthalpy. Okay. Energy added to the water. Okay, not internal energy, and enthalpy. Internal energy is the only one part of the only one term in the enthalpy. So enthalpy for 100 kilopascal just now. 100 kilopascal just now, enthalpy and HFG Okay, 2000. Okay, we take the evaporation enthalpy. Okay, because the liquid, the water is in the vaporization process. Okay, so we take this one, HFG 2257 kilojoule per kilogram. Okay, so and multiply with the 200 gram just now, or 0.2 kilogram. 0.2 kilogram, since this is in kilogram, so you have to convert it into kilogram. Okay. Uh, Okay, so 2257 multiplied by 0.2. Okay, everyone. Semua okay ke? Setakat sekarang, exercise 1 and exercise 2.
Sekejap, masih tengah tulis.
Okay. Yang lain, tadi ada lagi yang baru masuk. You guys alert kan? Our class is at 9 a.m. Okay. Tadi saya nampak nama Nabila something. Tak ada dah. Okay, 11, 12. So I give some time. So maybe you can, at the same time, you can start to look at the exercise number 3. Share this data balik. Okay. A rigid tank contains of 10 kilogram of water at 90 degrees Celsius. If the 8 kilogram of the water is in the liquid form and the rest is in the vapor form, determine the pressure in the tank and the volume of the tank. Okay, so I'll give you some times to think about it. Because I already show example 1 and 2. So try to do first number 3. Maybe I will call out someone or several people, several students. Okay, try to think about the example 3, okay? You can use the table that I give in the WhatsApp group. Actually, you can also search by your own self. Just search je. Okay. Okay, exercise 3, the first part is kind of like the same as the exercise 1 because you already look up at the table for temperature table, okay, at 90 degrees Celsius. So the values that you have to find out is the same actually, the same row as in exercise 1, okay. But I still want to ask. Okay, maybe Afiq Zufairi.
Yes, that.
Okay, Afiq, are you here? Are you okay? So first one, okay, 3A. We want to calculate the pressure in the tank, in the water tank. Okay, so what we have to do first?
I from from
Pak
what
sikit
I
lah, kita tak dengar.
understand from what I understand is uh, based on the table, right? So
Okay, so what is the
I'm
value? Can you read from the table?
70.183 kilopascal.
Okay, so you read which table?
The table A4.
A4, saturated water temperature table, because we have the value of temperature 90 degrees Celsius, okay?
Yeah.
The row ada 90 degrees Celsius row, okay. Okay, so just that. Okay, thank you, Afiq. So the same answers as the first one, because the temperature is the same. Despite the mass is different, but temperature is the same, so the pressure is still the same. So next one, okay, thank you, Afiq. Next one, volume of the tank. Okay, so there are two methods approach to solve this one volume, because we have of course we have the table, and then we are given with the mass. Okay, so maybe we try the first one first with mass. So I want to ask. Uh,
Doctor, I have a question.
yes.
For the volume of the tank, is the only way to get it by like the mass of the vapor, multiply the specific volume of the vapor and plus the mass of the water in liquid, and then multiply the specific volume of the water?
Mm-hmm. Yes,
Uh,
there is one method.
um, can we know the other method after later?
Yes. I will tell about it later. Okay. Okay. I will call out Umi lah, Umi Umaira. Okay. Okay. So okay. So how do you calculate the volume of the tank?
Saya tak buat yang volume lagi.
Tak apa. Mana-mana yang awak buat lah. Mana-mana method yang awak buat. Buat macam mana?
Saya tak buat volume. Saya baru kira pressure tadi.
Okay, tak apa. So okay. Bagi idea, bagi cadangan, you give idea how to calculate the volume. Can you think about it?
No, I don't know.
No. Idea. Tengok okay, look at the thermodynamic table just now. The same table for temperature table.
Yes.
Okay, so which row do we have to look up to? Mana?
Specific volume.
Specific volume, okay? At which temperature?
19.
Okay, 90 degrees Celsius. Okay, so we want specific volume. So value mana? Which value we will have to take? Ni this one lah.
Liquid. Liquid and vapor.
Vapor? Liquid and vapor. You mentioned, okay, both. Okay, so, okay, thank you, Umi. Since we have the value of the mass, 8 kilogram and 2 kilogram, so we take the saturated liquid specific volume and multiply with the mass of the liquid form, which is 8 kilogram, and the other one for vapor, assume 2 kilogram. Okay, 10 minus 8, 2 kilogram. So multiply both of this value, and then add it, and we get the total volume of the tank.
Let's say just multiply with the kg plus.
Sorry, tak dengar, tak jelas sangat. Apa macam mana?
It's just to multiply with the mass.
Yes. 0.001036 multiplied with 8 plus 2.3593 multiplied with 2, and total up, and then you get the value, the volume of the tank, which is around 4.7 meter cube. Okay. So another approach is that okay, thank you, Umi. Another approach, we use quality X. But still, in this example, we calculate X based on the mass given. Okay, based on the mass given, the 8 kilogram and 2 kilogram. So remember the definition of the quality just now. Go back to the definition of quality. Tadi. This one. This one. Belah. Okay, this one. Okay, the definition of the quality. So we have X equals to M vapor over M total. So M vapor is 2 kilogram. The rest is in the vapor form. Okay, 2 kilogram, and the total is 10. So means that X is 0.2. Okay, X is 0.2, and then we use this one, V average. Okay, to get the volume of the tank. So VF is from the table. VF is 0.001036. Okay, plus X 0.2 multiply with VFG. So here VFG, you have to calculate the difference of ada tak VFG sih? VFG is the difference between VG minus VF. So you still have to use both of the value, 2.3593 and 0.001036. Okay. Kalau I want to write here. Okay, apa tadi? So X, okay, first X is 0.2, okay, 2 over 10 kilogram, and then so we want to calculate V equals to VF plus X V FG. Okay, so VF is 0.001 just now. 0.001036 plus 0.2. Okay, so but this one VFG kita tak tahu, we don't know yet. Okay, so we have to calculate VFG, the normal calculation. So VG minus VF. So we still have to search the value in the table. Okay, VG minus VF, which is 2.3593 minus 0.001036. Okay, so obviously the value of the vapor is higher. Okay, so minus that, and then total up, and we get the volume of the average volume of the water tank, and multiply back with the mass 10 kilogram. So here you will get 0.473 meter cube per kilogram. Okay, not yet finished. Okay, because the specific volume, remember, is in per kilogram. So you have to change it to multiply with 10 kilogram. So we get 4.73. So by using, in this example, by using quality X is longer. The method is longer. Okay, because we need to calculate first the X and change it between the phase, etc. Okay. Okay. So next, we still have time, kan? Okay. Maybe last one. Okay. Determine the specific volume of R134A. So this one is the refrigerant that I talked about just now. So we have to search for other table. We cannot use the same table as water just now. Determine the specific volume of R134A at 1 megapascal and 50 degrees Celsius using the ideal gas equation of state. The compressibility. Oh, this one yang compressibility check. Okay. Wait.
Hello. Oh, sorry. Doctor, I think you are lagging.
Oh yeah, sorry. Yeah. Wait. It's not, I have to search for the the diagram table for R134A. Specific volume. Okay, so we have to use table A1. Table A1. This one. Sama tak? Okay, sama. Okay, I've shared in the WhatsApp group. Okay. So ideal gas equation of state. The PVRT. Okay. So we have R 0.0815 kilopascal from the table. If you look up at the table, refrigerant R134A, or the name is tetrafluoroethane. Okay, tetrafluoroethane. Okay, you look at the table. The gas constant is 0.08149 or 15 kilopascal a kilojoule per kilogram per Kelvin. And then okay. Critical point properties. Okay, ideal gas equation of state. Okay. So we have to calculate actually the specific volume, determine the specific volume. So from ideal gas equation of state, we have RT over P. Right, ideal gas RT over P. So R is 0. Is given here, so 0.8159 or 15. Okay, and T temperature is 50 degrees Celsius, which is we have to change it to Kelvin. Okay, the ideal gas equation of state is in Kelvin. Okay, because R is in Kelvin. Okay, so don't forget to change it. So we get 323 Kelvin over the pressure. So the pressure is 1 megapascal. So 1 megapascal. So we can use kilopascal because the R is in kilojoule or kilopascal. Okay, the R, kilojoule per kilogram per Kelvin. So we have to change this pressure in kilopascal. So 1000 kilopascal. Okay. So we have calculate the specific volume. So this volume is more or less the same, but not exactly as the actual value. The actual value is given here 0.02171, means the real specific volume of this refrigerant at this temperature and pressure. But we just want to see how much the answer deviate if you use the ideal gas equation of state. Okay, so we want to see how much the error, okay, between the actual and the ideal assumption. Okay, so we get around 0.026 to 263 from this using the ideal gas equation of state. So meter cube per Kelvin. So we can calculate the difference, the energy, the loss. Okay, the difference, the percentage of difference. So the percentage of difference normally we calculate the absolute value. 0.02171 minus 0.0263 and divide by the actual 0.02171. So you get the percentage of error or deviation around 20%. Okay, or 0.2. Okay. Compare the values obtained and determine the error involved in each case. Okay. Okay, so that is the error for the ideal gas equation of state by using that. Another one.
Sorry, doctor. May I ask where did we get the pressure 1000?
Okay, this is from here, 1 megapascal. Okay, so we change into kilopascal because the R, the gas constant, is given in kilojoule or kilogram or kilopascal. So it is in kilo. So we have to use the same unit for pressure. Okay.
So the 1000 is kilo, right?
Yes, kilopascal.
The value of the pressure no need to include.
The value of the what? This one. Okay, this one is actually for question B.
Oh, okay.
Actually, this value is not given in the example. I include it because we have to look at the table actually. Okay, but I already put in this slide because in case we cannot find the table. Okay. Okay, so the second one. Okay. The second one that use a compressibility chart. Okay. So this is the chart yang okay. The Z chart. This one. The compressibility chart to determine the compressibility factor. Okay. 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 Okay, so we first have to calculate the PR and TR, okay, from this reduced pressure and reduced temperature. Okay, PR and TR. So P, for example, just now is 1 megapascal. So over the critical point pressure, you can get from the table that I gave in the WhatsApp, right? R134A. Critical point properties for this R134A, temperature is 374.2 and 4.059 for the pressure. Okay, so from the value of the table, okay, oops. Okay. So from the value of the table, okay, we can read this value from the table A1. Okay, 374 and 4.067 or 4.059. Depends. Actually, this table depends on the version of the book actually. So the some of the values is slightly different because of the book has been printed with a newer edition. Sometimes the value is slightly different from the different edition. But it's okay. Get it the 4.059 from the table that I give, or for 4.067, which is the more newer version. Okay. So okay, we calculate TR and PR just now. Reduce pressure and reduce temperature because we want to use the compressibility factor Z. So TR, 50 degrees Celsius over TCR, and PR is 1 megapascal over PCR. Okay, so we get the value of PR and TR. Okay, so calculate that one first, and then we need the compressibility factor diagram. Mana nak guna yang this one? Cukup besar. Okay, so we get TR around 0.86 and PR around 0.25 or 24625. Okay, so from the compressibility factor Z versus reduced pressure diagram, so which is for TR around 0.86 or about kat bawah sikit okay, we have to kind of like extrapolate the diagram, and PR reduced pressure around 0.25. So from the diagram that I shared, it's a bit outside from the diagram too, but it's okay. I'll give the value Z. Okay, so so at PR 0.25 and TR temperature 0.86. So the value of Z is like coincide with other values at the top. If you look at the diagram given, okay, around Z around 0.84, 0.8 something. Okay, so we imagine that the diagram is extrapolated. Okay, line. So we have Z around 0.8, and then the generalized compressibility chart. Okay, we want to calculate the specific volume. So this Z is like the correction factor. So you have to multiply with the ideal specific volume that we get just now using the ideal gas equation of state. So V, the actual by using the compressibility chart, Z, and the V ideal. Okay, because Z is the ratio of the specific volume over the actual over the ideal. So if Z around 0.8 and the V ideal just now we calculated for A 0.026 0.026 around that. Okay, so this will be our volume, specific volume for by using the compressibility chart. Okay, so we get around 0.02221. Okay, meter cube per kilogram. Okay, so and then the same just now we calculate the error, the difference between 0.0221 and the actual value given here 0.0217. So we see the percentage. Okay, the difference is less than the first approach by using the ideal gas. It's around only 2% the error. Okay, for this B approach by using the compressibility chart. So this example just to show you that by actually by using the Z the Z factor, our calculation, the measurement is more approach the actual value. Okay, because the error is less, around 2%, less than 20% just now. Just to show that the ideal gas equation state have some error, have some errors. So sometimes if we can use the compressibility chart to search for the exact volume, okay, exact value of the refrigerant or of the fluid. Okay, but we still can use the ideal equation of state because it is a simplified version. Okay. Okay, I think that's all for today. Okay, exercise 5, you can try if you have time. Okay, so we have done 1 to 4. So, okay, save to files, save. Okay, stop sharing here. Okay, so I think that's all for this week. Okay, do you have any questions? Anything? Everyone okay?
Okay.
Ada soalan ke? Tak ada So still 13, total 13 of you. There's still one person, I'm not sure who, did not attend my class. Okay, it's okay. Okay, so we stop here. Thank you very much. So I'll see you guys next week, Thursday morning as usual. Okay.
Doctor, is there any attendance we need to take?
I didn't do any attendance. It's okay because since I record, so I
Right.
can look back at the recording and look at who attended.